Welcome to the Theta Oilfield Services Rod Pumping Optimization video podcast. This is John Zvinos. The following is a presentation given at the 2009 Permian Basin Artificial Lift Forum.
Failure analysis is a pretty broad topic. Had a difficult time narrowing it down. I'm going to narrow it down to the small portion of our field that I deal with is, of course, the sucker rod. Again, my name's Scott Malone, Norse Rods. Failure analysis, and during your failure analysis and what you do for your company, root cause, I hear it all the time. I want the root cause, I want the root cause. Corrosion is not the root cause. So that's just what, thank you, I appreciate it. What is a failure? A couple of questions that are going to create more questions whenever you get around to looking at them in your operation, and you need to kind of have an idea for what they are for you. What is a failure? What are best practices? What are best practices for Norm are not going to be best practices for you, I'm sure. So, when do you tolerate a failure? Never? Okay. Okay. Where would you not tolerate a failure? So, just things to look at. Is this a failure? No? Really? Is that a failure? And again, it seems like a silly question, but when it comes to your operations, you need to have a definition for that as well. For the original design for this piece of equipment right here, of course that's a big nut sitting on top of that bolt. It's probably failed many centuries or decades ago. But it's a yard ornament now. It's not failed. It's doing its job. So again, what do you call a failure? Failure analysis or investigation. Again, my little note up there, easier said than done, and a lot of these things are. And if you do it and you apply it to your operations, you've already realized that. It takes time, effort. More important to be objective than to arrive at a wrong conclusion quickly. You're going to compound, of course, your error if you look at that wrong. Need a plan for material, people, and processes. And all you people that put up with all these processes, y'all have heard all that before. Document, report failures and successes. Again, easier said than done. A lot involved in gathering that information. Understand your system. Oh, you're not doing that. Realize that a change in a component in the rod system, artificial lift, can affect the performance and service life of other components in the system. Seems like quote-unquote common sense. But we change stuff all the time and wonder why the rest of the system goes awry. Identify and understand the cost drivers. That's going to affect a lot of your decision making, how much you want to spend on failures or not. Again, the system we're going to be dealing with here, and mainly the one I'm dealing with, is the sucker rod. It's going to tie us between that pumping unit up there and that downhole pump. We're putting our product in a fatigue machine. Designed for loads and inhibit for corrosion. Make that one statement because it gets calls very frequently to need your corrosion-proof rod. I'm sure we have a salesman somewhere out in our industry that has sold you on a corrosion-proof rod. I don't know why. It's just, no, I'm not trying to point at anybody in particular. And the only reason I say that is because, like I say, you get calls pretty frequently for it. I have H2S, I have CO2. Yes, you do. And you have to deal with it. So, body failures. Most rod body failures are related to environmental and or operating conditions such as abrasive wear, corrosion, abrasion, corrosion fatigue. Sucker rod, it's pretty simple. It's no moving parts. I mean, at least with a pump, you've got all these moving parts you've got to deal with. Like I said, sucker rod's pretty simple. It's people that are complicated. Getting to apply this very simple bar to a fairly complex system. Its failures are listed individually and shouldn't be. Wrench square, the abrasive wear, corrosion abrasion. If any of y'all seen of our material, y'all have seen this little piece right here. Always list a mechanical damage, and at the end, workmanship defects. It happens. Upset taper, abrasive wear, bent rods. Typically going to have some flexing going on there. The cross-sectional area for this product right here gets drastically greater as it goes to that swelled up, that flared area there right there. The weak point should be the rod body as far as tensile strength is concerned. In the body, abrasive wear, bent, corrosion, abrasion, and we'll get into a couple of those in particular. And again, those areas for the larger part, where we have the large part of the rod being attached to the smaller part of the body, if there's any shock loading involved, that's going to tend to bend right in that one area. I don't dare try this other button here. I'll probably be changing things wrong. But if we break right in this area right in here, most likely we're taking this limber part right here as opposed to this more rigid portion here, and it's going to tend to want to break right there if we apply a lot of shock loads to this product. Corrosion engineering. We're going to talk a little bit about the materials, and many of y'all are probably aware of this. Corrosion fatigue can be prevented by a number of methods. Increasing the tensile strength of the metal or the alloy improves ordinary fatigue, but is detrimental to corrosion fatigue, particularly in a sour environment. We're more likely to crack once the pitting has already started. And so again, goes back to that thing a while ago that we looked at. Design for load, treat for corrosion. When a failure occurs, secure the sample. Again, this is a laundry list of things that are easier said than done. Document the location of origin. Note the condition of the sample. This is for you, because this is going to come. This well is probably going to come back to you again someday. You'd like to know what happened back here whenever this failed. Determine the completeness of the sample. Did I get an accurate sample? I have just one end of the sample. Is the other end all that important? Do I need that to make a good determination to stop repeat failures based on the information that I gather this time? Scale, hydrocarbon deposits, record the results, and then record the results. Corrosion byproduct. One of the first things that's going to be done when it shows up in my office, I'm going to do a hydrochloric acid spot test, detection for iron carbonate. If you bead blast the sample because it stinks before you bring it to my office or most anybody else's office that's going to look at this sample, this is a useless test. You're going to bead blast the iron carbonate off. We won't have it available to test. Most likely you already know whether you have CO2 in your well or not, but it's still a test that's going to be run in most cases. Going to look for when iron carbonate is detected, the corrosion attack will be CO2 related. The pitch shape, characteristic, and morphology will reflect such. There is a predictive model put together by NACE API that the yardstick is at partial pressure above 30 psi, indicates that there is corrosion. If it's between 7 and 30 psi, may indicate corrosion, and if it's below 7 psi, use a corrosion, it's considered non-corrosive. If you have a broken rod or you have a hole in the tubing that has a corrosion pit that's shaped like CO2, which is going to be deep with sharp pit edges on it, regardless of the partial pressure, you got CO2 corrosion. Again, this is a rule of thumb. In absence of data, that's when you use a rule of thumb. So, rule of thumb is nice to have, but the chemistry at the surface is what's going to be important as to where the corrosion actually happens. Spot test for detection of iron sulfide. Again, you probably already know you have it. You've already got safety issues. You've got safety procedures set up in your operation to deal with that being there. But this test is still going to be run. The procedure is at least 1 drop of acid solution on the sample, and looking for a canary yellow precipitate. This hydrochloric acid and sodium arsenate give you that yellow precipitate right there. Where does the hydrogen sulfide come from?
Rotten eggs.
All right, that's good. That's a good place for it to come from too, or at least it smells like it. I mean, when you start using your senses looking for it, that's exactly where you're going to come up with. It's either in many cases you're producing it. We drilled into it earlier, maybe decades ago. It was